Hello everyone, my name is Pallavi Sharma and I'm currently a research scholar under the supervision of Dr. Munish Kansal at Thapar Institute of Engineering and Technology, Patiala, India. So the title of my today's presentation is Computation of Invariant Subspaces Associated with Certain Eigenvalues Using an Approach Based on Metric Sign Function. So this is the outline. First of all, introduction, then some literature review, construction of a novel iterative method, convergence and stability analysis, then comparison of efficiency, and some numerical results, and final conclusion. So the concept of simulation-based engineering plays a crucial role in enhancing our understanding of the concept of invariant subspaces, which involves utilizing computational tools and techniques to simulate real world phenomena and analyze the behavior of systems under different conditions. The impact of invariant subspaces in the spectral theory of matrices is a well established concept. And in most of the problems found in linear algebra, stability of the problem is considered as a fundamental requirement for numerical techniques. In general, we can say that a satisfactory approximation method cannot be found if the solution of a problem is extremely sensitive to little changes in the data. So similarly, stability of invariant subspaces in comparison to eigenvectors of a matrix is a widely recognized phenomena in matrix theory. So let's understand what are invariant subspaces. If we have a square matrix A, then a subspace W is said to be an invariant subspace if the W is contained in W. So how can we compute these subspaces? So basically the problem is to find out a unitary matrix Q such that Q star AQ is equal to A11, A12, 0, A22, where these are matrix blocks and Q star represent the transpose conjugate of Q. Then span of Q is equal to W is the invariant subspace for A corresponding to the eigenvalues lying in the region R, where the region R is containing the eigenvalues of A11 and A. So now instead of finding out this unitary matrix Q, we can compute eigenprojection of invariant subspace using matrix sign function. So computation of invariant subspace using matrix sign function. So matrix sign function computes the eigenprojections of invariant subspaces corresponding to the eigenvalues lying in left half plane and right half plane described as follows. So if we have a square matrix A, then I minus sine of A by 2 is the eigenprojection onto the invariant subspace for A corresponding to the eigenvalues lying in left half plane. And I plus sine A by 2 is the eigenprojection onto the invariant subspace for A corresponding to the eigenvalues lying in right half plane. Once we have obtained the eigenprojection onto the invariant subspace, we can compute the subspace by finding out the orthonormal basis from obtained projector with the help of any rank revealing algorithm. But how can we compute this sign of A? Let's discuss a formal definition of matrix sign function and methods to compute this function. So before introducing the definition, let's recall scalar sign function defined for all complex numbers which do not lie on the imaginary axis. So sign of z is actually 1 for all complex number whose real part is greater than 0 and minus 1 whose all real part is less than 0. So after the generalization of this definition, we can introduce matrix sign function for all matrices which have no eigenvalue on imaginary axis. So for this, we will consider Jordan canonical form of A as PJP inverse, where J has two Jordan blocks, J minus and J plus. J minus contains eigenvalues corresponding to the left half plane and J plus contains the eigenvalues corresponding to the right half plane. Then sign of A can be written in this form given in equation number 3. But computing sign of A analytically is not an easy task. Here comes the importance of iterative methods. Iterative methods provide a practical and efficient approach to approximate the matrix sign function. Let's review some of existing iterative methods used for matrix sign function. So best known method to determine the matrix sign function is the Newton's method given by this equation number 4. It has order of convergence 2. Then a general family of matrix iterations was proposed by Kenny and Log using the paid approximant to the function f of xi with xi is equal to 1 minus xi square given by this equation number 5. Here P by Q represents the RS paid approximant to f of xi and its order of convergence is R plus S plus 1. There are some other well-known iterative schemes to calculate sign of A which belong to this paid family or the reciprocal family, like Newton-Schulz method, which can be obtained by giving the value of r is equal to 1 and s is equal to 0, and we will get this equation number 6. Also, another method is Heller's method that can be obtained by putting r is equal to 1 and s is equal to 1. Its order of convergence is 3. So, motivating from these methods, now we will construct our proposed method. So when it comes to the construction and importance of a new iterative method, then our first goal is to construct a novel iterative formula that should not belong to the paid family. And second goal is global convergence. In order to achieve these two objectives, here we propose our method given by this equation number 8. Why not will be the appropriate initial guess that we will discuss later. We can easily check that the proposed method does not belong to the paid family or their reciprocals. So first goal is attained. To achieve the second goal of global convergence, let's draw basins of attraction for the proposed method. So for this, we have considered a square domain -2, 2 by -2, 2 in complex plane with a mesh of size 256 by 256. So here these two white spots represents the zeros of equation y square minus 1, because for matrix sign function we need to solve this equation. And here this right hand side dark red color represents the convergence area corresponding to the 0, 1, and this light red color, pinkish color represents the convergence area corresponding to -1. Also this black area represents the divergence area. That is where the method diverges. So we can easily see that Newton-Schulz method is not globally convergent as it contains very large black area, while other three methods, even our proposed method, is globally convergent. So now in order to prove that our method will converge to the sign of the matrix, we have given this theorem. We will consider initial guess as A, which has no eigenvalue in the imaginary axis, then our proposed method will converge to sign of A. For proving this, we will consider Jordan canonical form of A, where lambda i's, lambda 1, lambda 2, lambda p are the eigenvalues lying on left half plane, and lambda p plus 1, lambda p plus 2, lambda and be the eigenvalues of A in right half plane. Then by the definition of matrix sign function, we can write this equation number 9. From here, we can get sign of J as this sign of lambda as a diagonal matrix. Now we will define a sequence dk given by P inverse YKP, where D naught is P inverse AP. Then we will form this equation number 11 from the proposed method. Since this is in the matrix form, so we will convert this to scalar as an uncoupled scalar iteration, which is given in equation number 12. From here, we can easily conclude that this dk plus 1 minus si by dk plus 1 plus si can be written as this in equation number 13. So we will get that limit of this value will actually approach to 0. Therefore, limit dk is equal to psi, that is sine of lambda, which implies that that sequence dk will converge to sine of j. Also, the eigenvalues of yk are mapped from kth iteration to k plus 1th iteration by the relation given in equation number 15, which was briefly explained at the starting of the proof. So in a similar methodology, we can easily get that this limit will also approach to 0, and hence it is easy to conclude that our proposed method will converge to sine of A. So here comes the convergence rate. The convergence rate of our proposed method is actually 4. For proving this, we have considered these relationships. These are actually the properties of matrix sign function, that is its square is always identity matrix and its inverse is equal to itself, and even power is always identity and odd power is itself. So that inverse part in our proposed method, we have named it as omega k. Then yk plus 1 minus s can be written in this form, yk minus 4 raised to power 4 minus 6s into omega k inverse. And hence, this norm is less than equal to raised to power 4, which implies that our proposed method has convergence rate equal to 4. Also, the proposed method is asymptotically stable. For this, we have considered the numerical perturbation generated at kth iterate given by this equation number 70. And since we are performing error analysis of first order, then every power greater than equal to 2 of delta k will be approximately equal to 0, and hence we will get this equation number 18. Now, delta k plus 1 can be written as in this form, that is, it is approximately equal to half of delta k minus half of s delta ks, and hence perturbation at k plus 1 of iterate is bounded, which implies that our proposed method is asymptotically stable. Now, another factor is efficiency, how efficient our method is. For this, we will calculate computational efficiency index given by this formula p raised to power 1 by c, where p is order of convergence and c is the total computational cost per iteration. So, in order to compare our method with other methods, we have given this diagram, which clearly shows that our proposed method has higher efficiency index. Also, we have provided accelerated version of our proposed method. If the iteration yk has very large eigenvalue for some k, then conversions may be slow in that case. We can accelerate the convergence of the proposed method by introducing scaling parameter given in this equation number 20. There are three types of scaling parameter: non-scaling, spectral scaling, and determinant scaling. We can use either of them. So based on these scalings, we have proposed our accelerated method given by this. So for numerical results, we have actually used spectral scaling. So here is the numerical. We have considered some randomly generated complex matrices, different sizes in mathematical, and we have compared the results based on iteration number and CPU time that are provided in these tables. So we can easily check that our proposed method has lesser number of iterations as compared to Newton's method, Halley's method, or paid iterations. Paid iteration of order 4 as well. So it is better than, as mean of the iteration is less than other methods. Also, accelerated proposed method has more lesser number of iterations. We have also compared the total computational time in seconds for performing these iterations. So clearly, in based on CPU time also, our proposed method is better. So here is the final conclusion. The investigation of computing an orthonormal basis for the invariant subspace corresponding to eigenvalues in a specific region has been done, focusing on the projectors obtained using metric sign function. We have constructed a novel fourth order iterative method for computation of metric sign function, which can be implemented to compute eigenprojections for invariant subspaces. Convergence analysis and asymptotic stability of proposed method has been discussed. Global convergence of the method was illustrated through machines of attraction. Numerical experiments have been performed to test the practical ability and superiority of the proposed scheme, which clearly represents that our proposed method is better than existing methods. So these are the references. Thank you.